Okay, guys, we're going to finish this up really quickly. I'm going to share my screen so I don't forget. And we are now here. We looked at some of the occlusion process. This is a slide. This is in the PowerPoint 6 on tornadoes. And I think it's easy to see here that the wall cloud still exists. We definitely have a lot of rain falling back here. And notice that there's a tornado developing down in this region. And so you can see the clear slot. The clear slot's full of rain. So rather than having a few big drops, we are now getting a lot of smaller raindrops. So we visually are obscured in seeing things. But you can still get a tornado, especially with a really low base. And this is kind of typical of an HP, is that we have these low bases. There's very little evaporation going on, so the temperatures stay warm and buoyant. Now, we're looking at a storm here, and this reminds me of the Plainfield storm that I chased. This is not the Plainfield storm, but notice that we've got a really good hook and a strong rear flank gust front right in there. So if I take that out, you can see where that gust front is. Okay, well, this picture is the Plainfield tornado on the right. And similar to this, I would have been standing right there looking southward. Okay, so I'm looking southward into this cloud feature here. Now, this is not a wall cloud, even though some of the initial thoughts were that was a wall cloud. This is the shelf cloud along the rear flank gust front. So given this, the tornado would have been right there, and I was really close to the tornado. In fact, I got knocked off the road with very high winds and knocked down power lines. So when we're looking at storms, I want you to think about what that last one is, and now we're looking to the north at a storm. Maybe there's the hook, right? There's the hook. And if you're looking to the north, what I'm seeing here is the rear flank gust front. So the rear flank gust front would be something around there. So that's what I'm looking at. And this might be a shelf cloud over here where the air is kind of going into it. But if there's a tornado, it's back here. So if there's a tornado, guess where it's going to be? It's going to be back here someplace. The problem is I can't see it because of the rain that's falling. So looking to the north, if I'm in the wrong spot, that's bad. Well, this picture is where we were. We were looking into the notch. And so we see this extremely wide tornado, about a half a mile wide at least. You can even see a little bit of the clear slot right in there. So if you look closely, you'll see that. And this is just showing you why HPs are so dangerous. Sometimes you have to look into the notch to see the tornado. And it was coming at us, and it was kind of scary being on gravel dirt roads in Kansas. But it gives you an idea of how difficult it is to spot HP storms. Now, we did talk about the lemon technique. Given that we went through it fairly quick, I'll give you a quick review. A lemon technique is the way that we identify storms in a moderate to strong shear environment, moderate to strong vertical wind shear. And when we see a storm going off, we're assuming it's going to have a tilt. And when we see the precipitation echoes vertically aligned here or here, we are thinking about a non-severe echo. So this is in the non-severe multi-cell mode. We see a bunch of storms here. These are small, circular, not too bad. Now this one starts to get a little bit bigger. So now we're starting to look at a storm like this that might be more significant. And we definitely see an elongation of it, so it's no longer circular. We have this strong reflectivity gradient, a little bit higher echoes, maybe at low levels, but certainly at the mid and upper levels, we see a higher reflectivity. The development of the weak echo region. Here's the storm now. It's building more upright. Before it was tilted over, so the top has shifted up shear. Okay. And we probably have some deviant motion, meaning it had been going maybe this way, and then it kind of turns to the right. And in that case, we're looking at deviant motion, and that usually means we got to be careful of this one. So at this point, you probably issue a severe thunderstorm warning. Here's an example of a weak echo region that's pretty nice. Weak echoes here, underneath much higher echoes. So this is where your updraft is, right? Your updraft is here. And we're seeing the cloud would look like this. Precipitation's coming out both ways, and then most of it's falling out in the forward flank like that. This one does show you some of the deviant motion. As I watch it loop, this one's got developing a hook and it's going definitely south of east, while the other storms are moving off to the northeast. So looking at how all the storms gives you an idea of the mean wind flow. And then to see a storm doing different, that's significant. Now at this point, we start to get a storm that's going to be at its maximum height, rock hard, tops all the way up. This thing is really bad. It has a bounded weak echo region in here. We've talked a little bit about this. Now, remember, and this is key, that it's the collapse of the B-word, filling in. So in other words, all these things become echoes. So the echo core gets filled in, and that's a collapsing B-word. That's an important word, collapse. And that may indicate an intensification, because when it collapses, you tend to get that surge in the rear of the storm. And that surge in the rear flank downdraft, which we can refer to as a DRC, the descending reflectivity core, will cause the acceleration of the rear flank gust front, and it wraps around that, and that wrapping around is the occlusion, and that's the clear slot that we visualize. Okay? There's an example of a B-word. There's the B-word on a PPI. This is the RHI. Another one, this is a big storm up here, but this storm over here definitely exhibits a bounded weak echo region. And that means intense updraft. Now, we did talk a little bit about this storm. This was an amazing storm, came overnight. But again, looking at the Lemon technique, we don't have any cross sections on this, but you'd be like, well, it's kind of got an inflow notch here. It's got that reflectivity gradient. So there's indications it's severe, and you might have thought, well, let's put a severe thunderstorm warning. But then when we couple it with what's going on at the velocity, definitely needs to be a tornado warning. Okay, now what's this? Now, this is fairly clear, I think. There is a well-defined hook echo right there, and that's this storm there. But I'm not doing the cross-section through this storm. I'm doing it through a storm to the north. And if you look very carefully, I've got weak echoes underneath much higher reflectivity. So that is a weak echo region. And what's happening here is I've got mirror image storms. Not exactly a mirror image, but if there was a hook, it would look like this. And this hook looks like this. Now, the storm is actually splitting, and when you get a splitting storm, you tend to get an anticyclonic storm to the north, and then a cyclonic storm to the south. And that's what this looks like, but you can see the weak echo region. So that's still a pretty significant storm. You can take a look at that one. Here's an example of a splitting supercell. One of my students took this picture. Here's the rain-free base, so the updraft is up here, then there's precipitation falling over here, but in the distance, I see precipitation falling on this side, and the updraft is on the north side. So here we have the south side, this is the north side, and we're getting a storm split right down the middle here, and they'll spin in different directions. So it's kind of a cool thing. Here's an example of a left-turning supercell, and we have, unfortunately, we put the watermarks on there a long time ago and can't get them off. So we have a wall cloud, and then we should think, well, where's the forward flank? Wait a second, that's north. Wait, here's the forward flank. And that's because this is a mirror image. Now, if you don't believe me, this next picture actually is a physical mirror image of this image. So we flip it around, and it looks just like we would expect of a supercell. The wall cloud, the forward flank precipitation, and this is actually a mirror image picture of this reality. So I think that's kind of a cool thing too. Now, tornadoes, lots of slang names go with tornadoes. So we might call a tornado that's really wide, maybe as wide as it is tall. We call that a wedge. This is more like a cone, or if it doesn't go all the way to the bottom, we call it a truncated cone. I'm not going to make you memorize these, but Sam, you're pretty good. I'm assuming that you know these things. This looks like an elephant trunk. I wish this was my picture. It's not. Here's maybe more of a very dusty You can see a little faint funnel in here, but remember, it's the debris being kicked up that's causing the visualization of the funnel. Here's a more traditional ice cream cone. Here's maybe a stovepipe. And again, really well-defined clear slot in here. Here's a weird wind-blown tornado. This one is definitely in the rope stage. Now, sometimes there's difficulty in spotting. You should know this. If you've got terrain, there's a lot of hills and trees, and you can make out the tornado in this one in a clearing. But if you were in the forest, it would be really hard to see that far apart. We were talking a little bit about that in terms of Mississippi and how difficult it is to see in the distance. At night, this is a tornado on a video that was captured in a flash of lightning, and it looks pretty obvious that there's a tornado here. Sometimes it will hit power lines, and so you'll get an explosion that will illuminate the cone. Now, we were watching this and we knew that was a tornado, but just because there's a power flash doesn't necessarily mean there's a tornado. It could be a branch from strong winds that went into the power transformer and caused a big spark. Here's an example too of just a quick flash of light, and there's all sorts of weird hanging down stuff. Looks like something there. This is actually just low hanging scud. It is not a tornado, but be careful at night. It's easy to convince yourself of things that aren't really there. Other tornado lookalikes, here we have some plow winds or dust being kicked up by outflow. Here, maybe some weird looking scud just kind of hanging down, not really rotating. But again, if you get caught unaware, all of a sudden you're like, oh, is that a tornado? You know, what about this? These are just rain shafts, even though they appear to be in the same location as you would expect a tornado. Here's some scud. Remember, scud stands for scattered cumulus under deck. And that's kind of interesting here, is we've got, it's not connected, it's not rotating, but it looked weird. And I think people were reporting it as a tornado. Now, what about this one? This one's a little bit more difficult, right? Because you definitely have something that looks like a wall cloud. And there's, what is this on the ground? Is that dust? I mean, it kind of looks like rain. So exactly what's going on here? Well, let's step forward into this and we'll see that we had rain falling. The rain started to diverge. What's this called? That's a rain foot. And the wall cloud is leaning toward this forward flank. And as that forward flank air starts coming out, it starts to get drawn back into the storm, and it connects the rain with the scud and the wall cloud. And so when I go backwards an image, that's what you end up seeing. So if you had not watched the entire sequence, it would be difficult. So for people who are spotting, sometimes you want to watch for a minute. Don't just look at a picture and think, what is it? Watch it and you'll see motions and actions. And that's the best way to understand this. If you said this is a tornado, you're a trained spotter. So you guys right now are really excellent trained spotters. And most spotter training is about an hour and a half, maybe 2 hours of teaching at a quick seminar. Think about how many hours we've spent on understanding thunderstorms. So you're really high-level advanced training by taking this course. So you should be proud of that. Now, before I let you go, I'm going to do one thing over here. I'm going to look at Blackboard. I'm going to look at the test to make sure if there's anything in there that I think you need to know. So I'm going to give you a little hint. So I'm looking at the essay portion of the test right now, and the long answers and essays. Oops, cancel. Let me edit that test so I can see it easier. I'm not going to share it with you, but I'm just going to talk through a few things. The first of those are things we've done. They're in the lectures. They're in the PowerPoints. You should be able to get them. Remember, number 4, we talked about when the B word is present. Well, what do you expect when there is the B word? And that's in the notes. It's in the lemon technique. And then what happens? When does a tornado happen? When does it begin? When something happens to the B word. So be aware of that one. During that phase of the B word, what do we may view on radar? Here, some of you might say donut hole or beware. That's not what I'm looking for. What's the feature when the beware stage goes away? We talked about it in class. It's small blank, it's an acronym. As this happens, it's common for the gust front to what? What does it do? Now, the last question here is the slinky feature along the rear flank gust front is called a vortex. Remember what it's called? Goes over. This results in two counter-rotating. You know that. And then what do you need on top of it to get the tornado? And what are you doing to the vorticity? So you should be able to figure that one out. I hope this is good. Now, essays, they're 20 points each. You have to put some good effort into them. First one's on the lemon technique, and I went through some of those big paragraphs. So write it up, summarize the lemon technique in your own words, use diagrams. That's how you're going to do this one. We talked about vorticity in a supercell. There's a lot of places for it. So you have a lot of options for this. Write well and you get more points. And then why do we have vorticity within a tornado? See how well you can put that. That's a tough question. Then we talk about the clear slot. We've gone through that. There's lectures on that. And then summarize the basic meteorological cause of the three different storm types. I'm not talking HP, LP, or classic. I'm talking about air mass, multicell, and supercell. So make sure that's just a clue. That's a hint for you to get that last part of the essay test. Okay, take your time, study that, put it all together, do that, and then go take the test online. Okay, guys, if you have questions, you can always give me a jingle or an email, and I will see you guys next week. Best of luck.